Now I'm going to show how to use the Shockwave method to calculate the total delay and maximum queue length. So first, I included the answers from the determinist queuing from earlier to compare with the Shockwave method answers. And we can start out with looking at this graph first. So I drew the first part of the graph here based on the given flow, arrival flow here. So it say at x0 there are 3200 vehicles per hour from t0 time equals 0 to 50 minutes. So at x0 there are 3200 vehicles coming in from 0 to 50 minutes. And because there is a constant flow of 400 at x1, beyond x1 there are 3600 vehicles coming in. And we know that the vehicles that left at 0 minutes did not encounter any congestion and was able to travel at free flow speed. So I drew the straight line here based on the density flow relation. So right here it shows that this equation represents uncongested traffic, and it's equal to Q equal 100 kilometers per hour times K. So the drivers travel at 100 kilometers per hour, and this segment here total is 10 kilometer. So 10 kilometer divided by the speed 100 kilometer is 1/10, and I convert it to the minute and becomes 6 minutes here. And we know that the bottleneck is right here because the capacity is decreased to 3200 from the 4000 here. That's why congestion started forming, because there are 3600 more demand coming in than the capacity here. So what we want to do now is find out the velocity or the slope of this shockwave here to find out how fast the shockwave is moving to bottom of the upstream here. And we know that the tail of the congestion meets with the vehicles that left at 15 minutes, because after 15 minutes there are 2,400 vehicles coming in, and which is less than the capacity of the bottleneck, and so Q will start to decrease. So we want to find out the velocity of the shockwave first, then where they meet here. So equation for the shockwave velocity is shown right here. It's Q1 minus Q2 divided by K1 minus K2. So Q1 is the flow from the upstream, Q2 is flow from the downstream here, and K1 is the density from the upstream here, and K2 is the density from the downstream here. So we're gonna use this given density flow relation to find out the density of its regions. So I'm gonna call this as a shockwave 1. Let me write down here in the black color. So B is the region of right here is uncongested traffic, so we're going to use this equation, and for the region C we're going to use the congested traffic right here. So it's equal to Q equal 100 kilometer per hour times K, and C is equal to Q equal 2500 minus 25K. So now let's plug in the flow here. So for B it's 3600. You have to divide it by number of lanes. So there are 2 lanes here, equals 100 kilometer per hour times K. So it'll be 1800 equal 100 kilometer per hour times K. k equals 18, and then you have to multiply by the number of lanes again, which will make it 36. And let's look at the region C. For Q, it is equal to the bottleneck capacity or the discharging rate, which is 3200 equal to, also you have to divide it by 2. So 2500 minus 25k, this is 1600 minus 2500 equal negative 25k. So this is negative 900 equals negative 25k, k equals 36, and times by number of the lanes is 72. So let's now plug it into the Shockwave equation. So it is Q1 minus Q2 divided by K1 minus K2. It is 3600 minus 3200 divided by the 36 minus 72, which is equal to 400 divided by negative 36 is equal to, let me put this in the calculator, it's 400 divided by 36, it is negative 11.11 kilometer per hour. So this is negative, the shock rate is negative, which means that it's increasing, and it's moving at negative 11.11 kilometer per hour. And now let's find out where these two lines meet, where the free flows travel from the 15 minutes meets the end of the shock wave. So we're gonna use the basic equation of the lines. So let's write it down here. We know the travel of the both line, the speed of the both lines. So for the shock wave, it will be the x location equals negative 11.11 kilometer per hour times t plus c. And then let's convert that into minutes divided by 60 here. And then for the free flow uncongested, that left at 15 minutes, it'll equal to x equal 100 kilometer per hour. Let's divide it into 60 times t plus c. And let's solve it, this equation first. So we know that we know the point of the line here. So it is at 6 and 10 kilometer. So we can plug that in to solve for the equation. So at 10 kilometer, negative 11.11 divided by 60 times by 6 plus c. It's 10 here. So 10 kilometer equal to negative 1.111 plus c. So c equals to 11.111, which makes the equation x equal negative 11.11 kilometer per hour divided by 60 times t plus 11.111. And let's start for the uncongested here. We know this data point, which is at 0 miles and 15 minutes. Let's plug in here. So x, let's write 0 equal 100 kilometer per hour divided by 60 times by 15 plus c. So 1, 4, 25, 0 equals 25 plus c, and c will be negative 25, which will make the equation x equal 100 kilometer per hour divided by 60 t minus 25. So what we're gonna do now is to find out this where they meet. We're gonna solve for both equations here. So let's write down x equal 100 divided by 60, t minus 25, and x equal negative 11.111 divided by 60 plus 11.111. Delete one here, and then subtract the other equation. So it'll be 0 equals 100 divided by 60 t plus 11.11 divided by 60 minus 25 minus 11.111. So this will simplify into 100 divided by 60 t. Wait, actually need to add them up. It'll be 111.11 divided by 60 t minus 36.111, and let's solve for the t here. 11.111 1 divided by 60 t, and then so it'll be 36.111 times 1160 equals t. And let me put this in the calculator. So 60 divided by 11.11 times 36.11 is equal to, so t is equal to 19.5 minutes. And so at 19.5 minutes, the drivers that left at 15 minutes, they will reach the end of the queue at the 19.5 minutes. And let's plug that in to find out where in the 10-kilometer segment they'll meet. So let's plug that into this equation. The x equal 100 divided by 60, 19.5 minus 25 is, let me put this in the calculator. So 100 divided by 16 times 19.5 is 32.5 minus 25 is 7.5. So when they reach the, so let me write it down here. So this data point right here is 7.5 kilometer in 19.5 minute is when they reach the end of the queue. Now we want to calculate the second shockwave, which will be positive because the less than the bottleneck capacity is flowing to the X3 now. So I wrote down the shockwave 1 velocity here, and let's calculate the shockwave, the velocity of second shockwave. Shockwave 2. So same thing here, it'll be Q1 minus Q2 divided by K1 minus K2. And we're gonna use the same density flow relationship again. So let's actually call this region D. So D is equal to Q equal 100 kilometer per hour times K, and C will be the same as we calculated. It's 2500 minus 25K, so it is 3200 divided by 2, 2500 minus 25K, so it is 1600 minus 25 equals negative 25k 900. Negative 900 is 25k, which makes k 32, and times by 2 lanes is 72. And let's calculate the D right now, and it's 2400 vehicles coming in equals 100. Let's divide it by 2 lanes. Kilometer times k, so it'll be 1200 equals 100 kilometer per hour times k. K equals 12 times by lanes again, it'll be 24. So let's plug it into the equation here. So it'll be 2400 minus 3200 divided by 24 minus 72. So it'll be 800 divided by 24 minus 72 is, so negative 48. 800 divided by 48 is positive 16.67 kilometer per hour. So what this means is that this is moving at 16.67 kilometers per hour. And now we want to know how long it would take the shockwave to the end. So this will be a simple calculation. So we know that velocity is moving at 16.67 and is trying to move 2.5 kilometers. So because it's 7.5 here, and this is 10 kilometer. So we would simply divide the distance by the rate, which is 2.5 kilometer, divided by the velocity of the shockwave, which is 6.67 kilometer per hour, which is, let me put this in calculator. So 2.5 divided by 16.67 is 0.149, but we want to multiply by 60 to convert into minute, which will be rounded to 9 minutes. And then now you want to add this 9 minutes from here to end of the queue to the 19.5. So it'll be 19.5 minutes plus 9 minutes is 28.5, which is the end of the queue. So let's write it down here. The queue. So Q ends at 28.5 minutes. So now we would simply draw a line from this end of the queue, because we know that in this the vehicles that reach this point right here would be driving at the free flow speed. So 28.5 minus 6 is 22.5. So let me draw a line here. Might look a little bit messy now, but it'll be at 22. Let me write it again. So it'll be at 22.5 minutes. So now we can finally calculate the maximum queue length. So the total vehicles in the queue is calculated by the distance here, the vertical distance here, times the density. So we already calculate the density of this C region here is 72, and this vertical distance is 10 minus 7.5, which is 2.5. So see, let me write total vehicle in queue equals 75 times 2.5 kilometer, which is 180 vehicles. So this is 180 vehicles, and if you actually compare it with the determinist queuing, it calculates maximum queue length as 100 vehicles. It is because, like I explained earlier, determinist queuing assumes that vehicles will reach the bottleneck at the free flow speed, and then Shockwave actually assumes that the queue will move down here, and then they will encounter this queue even before reaching the bottleneck. Now you want to calculate the total delay time. So total delay can be calculated by total travel time vehicle hour minus total free flow travel time. So it's basically subtracting the total free flow travel time from the actual vehicle hour. So let's start with the free flow travel time first. So let me write down total delay free flow travel time. So let's calculate how many vehicles are entered in this graph here first. So we know that there's 32 from 0 to 15 minutes, 2000 from the 15 to 22.5 minutes, and there's a total of 400 vehicles per hour, the constant flow per hour from x1. So we would write this as 30 at x0, it'll be 3200 times, because it's vehicle per hour and it only lasted for 15 minutes, so we would multiply by the 15 over 60 hour, this plus 2000 times 50. No, it's not 15, it's 7.5. The duration was 7.5 minutes. 7.5 minutes over 60. And x1 is at the ramp, which will be 400 vehicle per hour times, for a total of 22 minutes there were constant flow. So 22.5 divided by 60. And this will give you how many vehicles are there in total. So let me put this in the calculator. So 32 100 times 15 over 60 is 800, and 2000 times 7.5 over 6 is 250, which will make 1050 vehicles in total. So at x1, let me calculate this. 400 divided by 22.5 over 60 is 150 vehicles. So now that we have a number of vehicles, we want to calculate what is the total vehicle hour for the free flow travel time. So we will first set up the equation like 1050 vehicles times, they would take only 6 minutes to get to x3. So 6 divided by 60 plus 150 times, because they entered at x1, which is at 3.33, and this is like 6.67. They would only take 4 minutes to get to the x3, so it'll be 4 over 60, which is, let me put this in the calculator, 60, it's 105, and plus 10 is 115 vehicle hours in total. So now let's calculate the total travel time vehicle hour. So we will calculate this by calculating the area. We will calculate the area of its regions here. So let me divide this regions here, and let's call this E. So we would get area of the each regions and times by density. That will give you the vehicle hours. So we write it down here. So total vehicle travel time. So let's divide it into A, B, C, D, E. So let's first write down the density of its regions that we calculated earlier. So we know that this is at 72, 36, because they're uncongested, it's 100 kilometers per hour. So this will be 32, 24, and 20 here. So let's write down the density first. So A is at 30, I write it in black. So 32, B is 36, 72, 24, 20. So let's now calculate the area of A, which will be base times height. So 15 times the 3.33. So 15 times 3.33. And make sure that you divide the 15 by 60 because you want to calculate the vehicle hours in 15 minutes. So let's take a look at B here now. So B here, this region right here can be divided into two. So let's get area of such triangle and this parallelogram. So the base is still 15 because these are parallel. And the distance between right here is 7.5 and this is at 3.33. It will be, this distance between will be 4.17 kilometer. And the distance from here to 7.5 will be 2.5. So let's write down the area. So it'll be 15 divided by 60 times 4.17 for the parallelogram plus 2.5 kilometer times 15 divided by 60 times 1/2. And for C, we know that it's from 6 to 28.5 is a base. So base will be 22.5 and the height will be 2.5 here. So it is 22.5 divided by 60 times 2.5 times 1/2. And for region D, it is the bases from 15 to 22.5, so it is 7.5 here, and height is the same 4.17. So 4.17 times 7.5 divided by 60. And lastly, E would be 3.33 times 7.5 divided by 60. And I have the answers ready to save time. So first one will be 0.83, and this is 1.35, and this is 0.46, and this is 0.68, and this is 0.41. And now what you want to do is multiply density with the area, which will give you the vehicle hour, because the density is in the unit of vehicle per kilometer. vehicle per kilometer. So multiplying that with the area with the unit of kilometer per hour, which it will give you the vehicle hour. So density, which is vehicle per kilometer times kilometer hour, becomes vehicle hour. So you want to multiply this density here for everything. The same thing applies to everything. So I have the answers ready also, which is this is 26.67, this is 48.75, this is 33.75, this is 16.25, this is 8.33, and to get the total you have to sum all these up. So total vehicle hour is 133.75. So let's go back to the total delay equation here. So it's a total delay. As a reminder, total delay is the total travel vehicle hour minus total free flow travel time. So total travel vehicle hour is 133.75, and let's subtract this from this. So 133.75 minus 115, which is 18.75, which is the total delay. And if you calculate that with the deterministic queuing, let's go back here, it actually yields the same result. And this is how to use the Shockwave and queuing theory.